Welcome to this scientific lecture on gravity-free microfluidics. We're going to explore the fascinating physics of how droplets, bubbles, and capsules behave in the unique environment of space. Let me start with a fundamental question. What happens to fluid systems when buoyancy completely vanishes? On Earth, gravity creates density-driven flows. Lighter fluids rise, heavier fluids sink. This buoyancy-driven convection dominates many fluid behaviors. In microgravity environments like the International Space Station, buoyancy effectively vanishes. Surface tension becomes the dominant force governing fluid behavior. Here we see the contrast. On Earth, gravity pulls fluids downward. In space, surface tension pulls equally in all directions, creating perfectly symmetric systems. Let's understand the physics quantitatively. Surface tension arises from intermolecular forces at interfaces. Surface tension gamma is defined as energy per unit area, typically measured in millinewtons per meter. The force due to surface tension equals gamma times the contact line length L. Now let me ask an important question. What is the bond number and why is it so critical for understanding microfluidics? The bond number is the ratio of gravitational forces to surface tension forces. Rho is density, g is gravitational acceleration, L is a characteristic length scale, and gamma is surface tension. The bond number tells us which force dominates. When BO is much greater than 1, gravity dominates. When BO is much less than 1, surface tension dominates. On Earth, for typical droplets, BO is much greater than 1. On the ISS, with microgravity of 10 to the minus 6 grams, BO approaches 10 to the minus 6. Surface tension completely dominates. Let's examine how individual droplets behave in microgravity. This is where things get truly fascinating. In microgravity, droplets naturally form perfect spheres. This is because a sphere minimizes surface area for a given volume. The Laplace pressure difference equals 2 gamma over r. On Earth, gravity flattens droplets against surfaces. The shape becomes asymmetric, with a flattened base. In space, perfect spherical symmetry is maintained. This allows us to study pure capillary phenomena without gravitational distortion. Let's dive deeper into capillary-driven flows. The key is understanding the Laplace pressure. The Laplace pressure jump across a curved interface equals gamma times the sum of the inverse principal radii of curvature. This is the Young-Laplace equation. Here's a critical question. How exactly does curvature drive fluid flow in microfluidic systems? Pressure is higher in smaller bubbles and lower in larger bubbles. This pressure gradient drives flow from high curvature regions to low curvature regions. This is the fundamental mechanism of capillary flow. Experiments on the International Space Station have revealed remarkable behaviors in emulsion formation. An emulsion is a dispersion of one liquid phase in another immiscible liquid. Think of oil droplets in water. In microgravity, emulsions exhibit perfect monodispersity. All droplets have nearly identical sizes. This is because gravity doesn't cause creaming or sedimentation. On Earth, emulsions are typically polydisperse. Droplets coalesce, and gravity causes larger droplets to rise or sink, depending on density differences. In space, we achieve symmetric, stable emulsions with precisely controlled droplet sizes. This opens new possibilities for materials science and pharmaceuticals. Let's examine another important phenomenon, Ostwald ripening. This is crucial for understanding long-term emulsion stability. The Ostwald ripening equation describes how droplet radius cubed grows linearly with time. D is diffusivity, Vm is molar volume, C infinity is solubility, R is gas constant, T is temperature. Larger droplets grow at the expense of smaller droplets through molecular diffusion. This is driven by the Gibbs-Thompson effect. Here's the characteristic linear growth of radius cubed versus time. In microgravity, we can measure this process without convective interference. Now let's turn to bubble dynamics. Bubbles in microgravity behave fundamentally differently than on Earth. Here's an obvious but important question. Why don't gas bubbles rise to the surface in microgravity? Without gravity, there's no buoyancy force. Bubbles simply remain suspended wherever they form. They don't rise or fall. When two bubbles collide in microgravity, they can coalesce. The coalescence dynamics are purely controlled by surface tension and viscosity, with no gravitational drainage. The drainage time for the film between two bubbles scales as mu h0 squared over gamma, where mu is viscosity and h0 is initial film thickness. This understanding enables revolutionary microreactor designs that are impossible on Earth. Microreactors are chemical reactors with characteristic dimensions below 1 millimeter. They offer enhanced heat and mass transfer. On Earth, gravity causes significant flow instabilities in microreactors. Density differences lead to unwanted mixing or phase separation. In microgravity, we achieve pure capillary control of multi-phase flows. This enables precise manipulation of reagent droplets and reaction products. Here's a conceptual microreactor with a droplet train flow. Each droplet acts as an isolated microbatch reactor, traveling through different temperature zones. To design these systems, we need another dimensionless number, the capillary number. The capillary number equals mu u over gamma, where u is characteristic velocity. It compares viscous forces to surface tension forces. At low capillary numbers, surface tension dominates and droplets remain spherical. This is ideal for maintaining droplet integrity. At high capillary numbers, viscous forces deform droplets. This can be useful for enhancing mixing within droplets. This graph shows droplet deformation versus capillary number. At very low Ca, deformation is minimal. As Ca increases, deformation grows significantly. Another crucial aspect is contact angle and wetting behavior. This determines how fluids interact with solid surfaces. Young's equation relates the contact angle theta to the interfacial tensions. Gamma SV is solid vapor, gamma SL is solid liquid, gamma LV is liquid vapor surface tension. On the left, a hydrophilic surface with contact angle less than 90 degrees. On the right, a hydrophobic surface with contact angle greater than 90 degrees. In microgravity, these angles are perfectly symmetric. Let's explore capsule formation, specifically double emulsions. These are droplets within droplets. A double emulsion consists of small droplets of one phase contained within larger droplets of a second phase, all suspended in a third continuous phase. Here's a schematic of a double emulsion with a core shell structure. The inner droplets are perfectly spherical in microgravity, enabling precise encapsulation. Let's discuss practical applications of gravity-free microfluidics emerging from ISS research. In pharmaceuticals, microgravity enables production of drug particles with unprecedented uniformity. This improves bioavailability and dosing consistency. Material science benefits from novel composites and metallic foams with uniform cell structures impossible to produce in Earth's gravity field. Understanding capillary flows in microgravity is critical for spacecraft fuel tank design. Surface tension positioning of fuel is essential for reliable engine restart in orbit. Here's a fuel tank with capillary veins. These structures use surface tension to position liquid propellant at the tank outlet, preventing gas ingestion during engine firing. Looking to the future, gravity-free microfluidics will enable in-situ resource utilization for deep space missions. Future missions will extract water from lunar or Martian soil. Understanding capillary flows in regolith is essential for designing extraction systems that work in reduced gravity. Metal refining in space could provide construction materials without launching them from Earth. Capillary-driven separation processes offer energy-efficient purification. The Weber number, RHOU squared L over gamma, compares inertial forces to surface tension. It's crucial for designing two-phase flow systems in partial gravity environments. Let me summarize the key insights we've covered in this lecture. First, surface tension becomes the dominant force when the bond number approaches zero in microgravity environments. Second, perfect spherical droplets in space enable fundamental studies of capillary phenomena without gravitational distortion. Third, Marangoni flows become the primary mixing mechanism, driven by surface tension gradients from temperature or concentration variations. Fourth, the ability to create highly monodisperse emulsions opens new applications in pharmaceuticals, materials, science, and chemical processing. Fifth, experiments on the ISS directly inform the design of critical spacecraft systems like fuel tanks and thermal management. In conclusion, Gravity-free microfluidics represents a unique laboratory for studying fundamental interfacial phenomena. By eliminating buoyancy-driven complications, we can isolate and study pure capillary effects with unprecedented clarity. The knowledge gained enables technologies that are either impossible or impractical in Earth's gravity field. As humanity expands into space, from the Moon to Mars and beyond, the principles of gravity-free microfluidics will be essential for life support, manufacturing, and resource utilization. Thank you for joining me in this exploration of gravity-free microfluidics. The physics of droplets, bubbles, and capsules in space continues to reveal surprises and opportunities for innovation.